Students, today we are going to discuss next points from the topic instruments. Previously we discussed different front panel controls of CRO and construction of cathode ray tube, which is heart of the CRO. Now we are going to discuss how the CRO is constructed with the help of block diagram. In this session we are going to discuss different blocks with its detailed explanation. There will be the question in the examination: explain the block diagram of CRO with neat labeled diagram. So in this session we are also going to discuss applications of the CRO. So let's start with the block diagram of the CRO. Here this is the schematic block diagram of the particular cathode ray oscilloscope. The input which is to be measured or which is to be observed on the CRO screen is given as a Y input. This Y input is nothing but any signal which we want to measure or test or observe on the CRO screen. This Y input may be AC or may be DC. This is given to the vertical attenuator which calibrates the input voltage. And now the signal is given to the vertical amplifier which increases the strength of the weak signal before applying to the vertical deflection plate. Here this vertical amplifier gain is controlled by using volt per division knob, and this volt per division knob is available on the front panel of the CRO. This vertical amplifier output provides the vertical deflection of the electron beam according to the amplitude. So its amplitude is controlled by using volt per division knob. This volt per division knob therefore used to adjust the amplitude on the CRO screen. Some sort of delay is introduced. This is for the synchronization of the synchronization of the signal which is applied to the vertical deflection plate as well as horizontal deflection plate. Because in case of the horizontal section there are different number of circuits which require some sort of delay, and therefore the electron beam may be deflected in different time intervals. So it will distort the waveform. Therefore the signal to the vertical deflection plate as well as to the horizontal deflection plate, which affects the deflection of the electron beam on the CRT screen. Therefore this delay is introduced, due to which the signal applied to the vertical deflection plate and signal appeared to the horizontal deflection plate simultaneously affect the electron beam, and we will get the undistorted output. So remember that for the synchronization of the signal for the vertical deflection plates and for the horizontal deflection plate, we require some sort of delay in vertical section. In horizontal section there are different number of circuits. So we will discuss later on what is the horizontal section. So when the signal is available on the vertical section, that sample is taken and given to the trigger circuit. When the input is available, this trigger circuit generates one trigger pulse which will initialize the time-based generator. This time-based generator is nothing but one of the sawtooth oscillator constructed using UJT. This generates positive and negative ramps. So its output is sawtooth waveform. So positive ramp is called as trace time and negative is called as retrace time. So this time-based generator provides the particular frequency sawtooth waveform, and that signal is given to the horizontal amplifier, and that horizontal amplifier increases strength of that signal, and after amplification it provides it to the horizontal deflection plate. This horizontal signal and vertical signal are simultaneously affect the electron beam, and the electron beam is deflected horizontally as well as vertically. This horizontal amplifier section consists of one more facility that is called as a phase inversion. It can provide the positive phase as well as the negative phase. So this is about the internal time-based signal. Sometimes we have to connect the external triggering circuit, and that is applied to the horizontal amplifier, and therefore there is one of the switch called as internal external knob. When this position of the switch is at the internal position, the output of the time-based generator is connected to the horizontal amplifier. But when we want to connect the external trigger or external horizontal signal, then it is applied to the X input of the CRO, which is available on the front panel of the CRO, and that X input is connected as a horizontal signal, and that signal is now given to the horizontal deflection plate. Means this switch, internal external switch, defines whether we have to connect to the time-based generator or whether we have to connect the external input signal. The amplifier gain is controlled by using time per division knob. This time per division knob defines the horizontal deflection of the electron beam. If the gain is higher, the electron beam is deflected horizontally in maximum direction. So during the trace time, electron beam strikes on the CRT screen, but while during the retrace time, means again electron is coming back to the original position, that time the blanking circuit will be activated, and that blanking circuit will provide very high negative voltage to the control grid, and therefore there will be no electron towards the CRT screen, and screen becomes blank because all the electrons are reflected back, and this is the function of blanking circuit. So blanking circuit provides the high negative control grid voltage during the retrace time period. So these are some blocks. This section is called as a vertical section. This section is called as horizontal section. As we consider here, after the sample input is available, the trigger pulse generates one trigger. It's a trigger circuit generates one trigger pulse, which will initialize the time generator and start the sawtooth oscillation. So there will be some delay required after the trigger pulse is generated to initialize the time-based generator, and therefore some sort of delay should be introduced in the vertical section to synchronize the vertical input as well as to the horizontal input to the deflection plate. So in case of the CRO, we required two different types of power supply. This is one of the high voltage power supply which is used for the CRT, where the accelerating anode, pre-accelerating anode, focusing anode and control grid, this requires high voltage power supply. But rest of the circuit requires the low voltage, means this trigger circuit, time-based generator or vertical alternator requires the low voltage power supply. So this power supply section consists of high voltage power supply as well as low voltage power supply. Low voltage is used for the rest of the circuits, and CRT is connected to the high voltage section. So this is the block diagram of CRO, in which CRT is the heart of the CRO. So when input, which is to be applied to the Y, which is to be observed or measured on the CRO, this is given to the vertical alternator. The gain of the vertical amplifier is controlled by volt per division knob, which some sort of delay is introduced for the synchronization of the signal applied to the vertical as well as horizontal deflection plates, and that delay line signal is, after delay, it is provided to the vertical deflection plate. In the horizontal section, when the sample input is available, trigger circuit generates one trigger pulse which will initialize the time-based generator, which generates the positive negative ramp that is called as a sawtooth waves, and this consists of UJT, and that signal is given to the horizontal amplifier, and that horizontal amplifier signal is given to the horizontal deflection plate. So this is called as horizontal section. So the blanking circuit provides very high negative voltage during the retrace period. Therefore, there will be no disturbance of the waveform on the CRT screen. And this is the power supply section, which consists of high voltage and low voltage power supplies. High voltage power supply is required to the CRT cathode ray tube, and the low voltage power supply is used to the rest of the circuits. So this is about the block diagram of CRO. After discussing this, we are going to discuss what is the application or what are the applications of the CRO? CRO can be used for the different applications. CRO is nothing but one of the versatile instrument which can be used for the measurement of AC voltage. It can be used for the measurement of the DC voltage. It can be used for the measurement of AC and DC current. But here current can be measured in the indirect method. We cannot measure the current directly through the CRO because its input resistance is very high. Means its input impedance is high, hence we cannot measure the current directly by using the CRO. CRO can be used for the measurement of the frequency of unknown signal. It can be used for the measurement of phase difference between the two input signals, provided both signals should have same frequency. There are different methods for the measurement of the frequency and phase. Frequency can be measured using the direct method, or it can be measured using the Lissajous pattern method. Phase measurement can be done using the Lissajous pattern method. It can be also used for the detection of nature of the waveform, means whether the signal is square wave, whether the signal is sine wave, triangular wave, etc. We can find out the shape or nature of the waveform also. The first application we are going to discuss how to measure the DC voltage using CRO. Before that, we already discussed that there will be one more control panel which is available on the front panel, and that is called as a volt per division knob. Suppose the scale for the volt per division knob is adjusted at the 2 volt. Then it indicates that the number of divisions, suppose these are the graticles 1, 2, 3, 4, these are the graticles available on the CRT screen. So one division is equal to 2. One division is equal to 2. That is the value of the graticle in when that is the 2 volt. Suppose this is of 1 volt, then this 1 centimeter is nothing but 1 volt. Here 1 centimeter is nothing but now 2 volt. Now suppose this is the reference line, reference point, and your applied signal, when you applied the signal, this reference line moved towards the upward direction, and now here we can see that it is deflected in upward direction by 2 divisions. Here 1 division is nothing but 2 volt. 1 centimeter is nothing but 2 volt. And how it is deflected? 2 divisions. Number of divisions are 2. 1 division and this is 2 division. So 2 into 2 is nothing but 4 volt, because 1 division consists of 2. Another consists of 2. So 2 how much? 4. Got it? See once again here, this is the reference line. When we applied the input signal, suppose the waveform moves in the upward direction. Number of divisions are 1 and 2. Number of divisions are 2. And this volt per division knob scale is of 2 volt. So each division is nothing but 2 volt. That is the value. And this division is also nothing but 2 volt. Means 2 plus 2, that is equal to 4. So we can find out the DC voltage by using number of divisions on the vertical scale multiply by time per division, volt per division knob. So 2 into 2, that is nothing but 4 volt. Suppose this is 1 volt, then 1 division is nothing but 1 volt. So 1, 2 into 1, that is equal to 2 volt. So next, so DC voltage can be measured using vertical displacement in centimeter, means number of divisions on the vertical section into volt per division scale, which is available on the front panel of the CRO screen. Suppose this reference line move toward the downward direction. This indicates that this voltage, applied voltage, is negative. Means this waveform or this signal moves in the upward direction, the applied voltage is positive. This is positive sign. And when it moves toward the downward direction, the voltage will be negative. So depending on the displacement, upward or downward, we can define the value either positive or negative. So this is one of the method for the measurement of the DC voltage. Similarly, we can measure the AC voltage using the CRO, that is nothing but Cathode Ray Oscilloscope. Same, suppose there is a one of the signal which is available on the screen, that is your sine wave. This is one of the nature. It may be triangular wave, it may be square wave, etc. So suppose the waveform we observed like this. The AC voltage can be measured in different ways. One of the method is we can measure the peak voltage. Peak voltage means it is the voltage measured from the reference x-axis towards the any one of the peak, either towards the positive crest or towards the negative trough. So we are here taking one of the peak voltage which is measured from the reference x-axis towards the positive peak. So number of divisions covered by the wave on the from the reference axis is 1, 2 and 3. So how many number of divisions are there? 3 divisions are there, and each division has the value of 5 millivolt. So number of divisions are 1, 2 and 3, and multiply by volt per division scale. So that is 5 millivolt, means 5 into 3, but how many is 15 millivolt, that is the voltage. Suppose we measured in downward direction 1, 2 and 3. So number of divisions are 3 and volt per division scale is 5 millivolt. So 15 millivolt, that is the voltage. If we want to measure the peak to peak voltage, peak to peak voltage means the voltage from this positive peak towards the negative trough. So that voltage is called as peak to peak voltage, VPP. Either we can find out the VP, and from that we can find out VPP. VPP means VP plus VP. So 2 times VP is nothing but VPP. So 15 millivolt plus 15 millivolt, that is nothing but 30 millivolt. That is the peak to peak voltage. Also we can find out number of divisions on the vertical section 1, 2, 3, 4, 5 and 6. 6 into 5, 30 millivolt. So that is the vertical division into volt per division scale. So 30 millivolt is the peak to peak voltage, and VPP is nothing but 2 times VP. Therefore its half is 15, that is nothing but peak voltage. So also from this we can find out RMS value of the AC voltage. What is the RMS? RMS means root mean square value. Root mean square value is nothing but peak voltage VP upon root 2, or 0.707 into VP, because 1 upon root 2 is nothing but 0.707, and that if we multiply this peak voltage by 0.707, we will get RMS value. This RMS is measured at the angle of 45 degree of the sine wave. So in this way we can find out the AC voltage, means we can find out the peak voltage, we can find out the peak to peak voltage, and from this also we can find out the RMS value, root mean square value of the of the waveform. So in this we can measure the AC as well as DC voltage. So in this we use volt per division knob, which is used to calibrate the vertical divisions. If this is of 10 millivolt, then one division is nothing but 10 millivolt, 20 millivolt, 30 millivolt, 40, 50, etc. If this is of 1 volt, then one division is nothing but 1 volt, 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, etc. If it is of the 2 millivolt, so one division consists of 2, 4 millivolt, 6 millivolt, 8 millivolt, 10 millivolt, 12 millivolt, etc. So this defines the value of 1 centimeter or 1 division. Also we can find out the frequency of the signal. This is the one of the direct method. Here we are going to discuss the horizontal deflection of the waveform, because number of cycles per second is nothing but frequency. So here we are going to use time per division scale, which defines the value of horizontal division 1, 2, 3, 4, 5, 6, 7, 8. These are the horizontal divisions, and this time per division knob defines the value of each division. Means suppose this is at the 10 millisecond, then the value of this is 10 millisecond. Value of this is 10 millisecond. means 10, 20, 30, 40, 50, 60 millisecond. These are the calibration of the. Suppose number of divisions on the x-axis. How are number? Horizontal axis 1, 2, 3, 4. This is the division covered by one cycle. So that is measured in time, means seconds. So one division is nothing but 10 milliseconds according to our time per division scale. So how many divisions are covered here? 1, 2, 3 and 4. 4 divisions. So number of divisions on the x-axis by the one cycle multiply by time per division knob is nothing but time period, that is called as a t, and the reciprocal of time period t is nothing but frequency. So we got the time required to complete the one cycle. 1, 2, 3, 4. 4 into 10, that is the 40 millisecond. 40 millisecond, 1 upon 40 millisecond provides the frequency like this. So number of divisions on the x-axis for one cycle multiply by time per division scale, that provides the total time period t, and by reciprocal of this time period we will get the frequency, and that frequency is measured in hertz. This is one of the direct method used for the measurement of frequency. So one of the another method, that method is called as a relative method. It is it is measured by using Lissajous pattern. So now we are going to discuss that method. When we want to measure the unknown frequency by using the CRO, one of the known frequency signal, whatever it may be, 1 kilohertz, 2 kilohertz, 3 kilohertz, that is applied to the X input of the CRO. Means that time your internal external knob should be at the external position. So external position knob and provides the external X input to the horizontal deflection plates. So that X input, that is called as the known input signal, Fx, is provided to the horizontal deflection plate through X input of the CRO. An unknown frequency signal that is connected to the Y input of the CRO, and that is given to the vertical deflection plate. When both the signals simultaneously applied to the CRO, some patterns are observed like this on the CRO screen, and depending on this we can find out the unknown frequency signal. So now we'll see. Suppose by connecting known frequency signal to the X input of the CRO, an unknown frequency Fy, which is to be measured, is connected to the Y input, and Fx is the known frequency signal. Fx is known and Fy is unknown frequency signal. And suppose the pattern is observed like this. So number of loops cut by the x-axis, 1, 2, 3 and 4. How many number of loops cut by the x-axis are there? 4 loops are cut. And here this is given here, number of loops cut by the x-axis, that is 4. And how many number of loops cut by the y-axis? That is only 1. So number of loops cut by the y-axis is 1. So from this we can find out the unknown frequency. So Fy is unknown frequency connected to the Y input. Fx is known frequency signal. Number of loops cut by the x-axis and number of loops cut by the x-axis. We can easily find out here. Similarly, sometime the pattern is observed like this. So here number of loops cut by the y-axis is 1, 2 and 3. So here we will get here 3. And for the number of loops for the x-axis, there is only 1. This is known frequency signal, that is Fx. Unknown frequency we can easily find out. Means Fx is moved here, we can find out Fy, that is nothing but unknown frequency signal Y. These are some another patterns. From using we can find out the frequencies, unknown frequency, after connecting the known frequency signal to the X input and unknown frequency signal to the Y input. So more Lissajous pattern for our observation. So this pattern will be like this. See here how the electron beam is strike on the CRO screen to observe the unknown frequency by using Lissajous pattern. After applying the X input signal to the X input of the CRO, and that is nothing but known frequency signal, and unknown frequency signal is connected to the Y input, and some sort of here waveform is observed here. So one more application of the CRO is measurement of phase difference between the two input signals, because sometimes it may happen that there are two or more input signals or more signals are available in the circuits. So we have to find out the phase difference between these two. But there should be one condition that should be satisfied, and that condition is both the signals should have same frequency. Then and then only we can measure the phase difference between the two signals. Means if the signal, one of the signal is of 50 Hertz, so another signal should be of 50 Hertz. Then and then only we can measure the phase difference between the two input signals. So when we applied the one of the input signal to the X input and another input signal to the Y input for the phase measurement, if we observed one of the diagonal line like this, so we can say that both signals should have same frequency, same phase, means 0 degree phase difference or 360 degree phase difference will be there in case of both the signal. So both have same phase, means 0 degree phase difference is there. After applying the signal, both the signals X and Y, suppose the circle is observed on the CRO screen, then we can say that the phase difference is of 90 degree or 270 degree. And if the diagonal line like this we have observed, then we can say that these two signals are 180 degree out of phase, means phase difference is of 180 degree. Means if the signals have both same phase difference, means 0 degree phase difference, we'll get the diagonal line like this, and the signal having 180 degree out of phase, we will get the diagonal line like this. And if the signal the pattern is like circle, then the phase difference is 90 degree or 270 degree. But it may happen that the phase difference is different than the 0 degree, 90 degree or 180 degree. Then some sort of pattern like this is observed. So we can also measure the phase difference other than this. So how we can find out? Suppose the waveform or suppose the pattern is observed like this. Then we know that theta is equal to sine inverse of A upon B, where A is nothing but the height of the pattern from the reference point where it cuts to the Y. And another one is B, that is the height from the reference point towards the maximum height of the pattern. So this is the B and this is the A, and from that we can find out theta is equal to sine inverse of A upon B, because sine theta is equal to A upon B. So using this we can find out the phase difference, which may be other than 0 degree, 90 degree and 180 degree. So means 45 degree, 60 degree, 35 degree, whatever it may be. And that theta we can find out using this Lissajous pattern. So all these questions are available in this book, book is Simplified Electronics by myself, and will easily get the answers of all these in simple manner, which can give you the maximum score in the board examination. So go for this book for the rest of the questions and answers. On this section or in this session we discuss about the construction of the CRO with the help of block diagram. We also discuss about the applications of the CRO, that is frequency measurement, phase measurement, one of the direct method, and another method is Lissajous pattern method. Also we can find out how to measure the AC voltage, DC voltage by using this. One more point is remained there, that point is called as current measurement. So we will also discuss that in next part. So here there will be the question in the board examination: with neat table diagram explain the construction of CRO. Explain how frequency can be measured using Lissajous pattern. How voltage can be measured using CRO. explain how phase difference can be measured using Lissajous pattern, and how the RMS value of unknown AC voltage is measured with the help of CRO, and explain in brief. So up to now we discuss applications of the CRO. Next session we will discuss further part. Thank you.